Welcome to a video on feedback, and in this video we're going to have a look at the voltage amplifier. So for the voltage amplifier is the series shunt topology. So the mixing happens in series and the sampling happens in shunt or in parallel with our amplifier. So for our voltage amplifier, our input impedance will increase when we apply our feedback, and our output impedance will decrease when we apply our feedback. So, on to some basic figures. So, if we have a voltage amplifier and we apply a feedback network, our measurement of our output should happen in parallel or in shunt. So, here is a load. Here is some measuring network, and here is the output of amplifier, and you would see that all three of these are indeed in parallel. Okay, so the measurement happens in parallel. The feedback, everything happens in series. So you can see that there is a kind of a loop here at the input. Right. So let's have a look at two voltage amplifiers with feedback applied. The first one that should be normal is the non-inverting configuration of operational amplifier. So the output you would see is sitting right here in parallel with these two resistors of the feedback network, right? So we have our output voltage, and then it goes into a voltage divider, which gives us a fraction that is our feedback voltage, right? So for voltage amplifiers, we will have voltage dividers in general to do our feedback. And here at the input of the amplifier is added to our feedback voltage, and it happens in series. So the measurements here happens in shunt, and the feedback is happening in series. Ideally, the input impedance here is infinite, and ideally the output impedance here is 0. So that is our first voltage amplifier with feedback. The second one here is two common source amplifiers, that's cascaded, and then it is into a feedback network to stabilize it, and you'll see again that this is a voltage divider being used, and the output is being measured in parallel with the output, and the feedback here is happening in series with the input. Right. So these are also the two problems that we are going to have a look at the end of this presentation. Right. So the rules for getting your beta network and your gain and whatever you need to find to do your feedback is you are going to include your source and your load in your analysis. Right, so with your basic amplifier, you're going to include these effects. Also, here you'll find that there is R11 and R22, which is the effect from your feedback network. So your feedback network is typically resistive, and their effects will be included in your amplifier. So in the process of determining the gain of your amplifier, you will include all the effects. Right. So check this out. All the resistors on the input side is added in series. All the resistors on the output side is in parallel, series shunt. Okay, so the naming of the topology can help you to remember what to do with your amplifier. Right, so first let's have a look down here at the feedback network. So the feedback network should have a voltage input, it should have a voltage output. Okay, so to find the beta network, we need to find VF over V out, and that is our beta network. Now, R11, the influence of the feedback network on the input side of amplifier. For that, we will short this voltage source right here and see what we can see looking into the amplifier like that. And that will give us R11. R22 is when we open circuit the output right here and look into this network and see what impedances we are seeing. That will give us R22. So the first order of business with most of these amplifiers will be to find R11, R22, and your beta. Then with R11 and R22, find the gain of the amplifier, including your source and load, if the source and load is available. Right, and then if you have determined A and beta, you can find your closed loop gain or your feedback gain AF, the input impedance with feedback applied, and the output impedance with feedback applied. So the best way to typically do this is to go with an example. So first example is we take an op amp, we put it in the non-inverting configuration, we apply two feedback resistors of 1 meg and 1 kilo ohm. We're driving a 2 kilo ohm load. We have a signal resistor of 10 kilo ohms, and the op amp specifics is 10 to the power of 4 volts per volts, a differential input impedance of 100 kilo ohm, and output impedance of 1 kilo ohm. Alright, so step 1 is to determine the gain of amplifier, the beta network, the input and output impedance of the amplifier, which includes all of the effects. So this is R out is all the outputs in parallel, and R in is all the inputs in series. Then there is two more definitions. So we have RIF and ROF. That is the input and output impedance with the feedback applied. So that is when we multiply or divide by 1 plus A beta. R in and R out is input and output impedance of amplifier as you know it. So those are excluding the effect of R sig and R load like this. Okay, so first step is to find all the amplifier specifics without the feedback applied. Note that the feedback resistors will be included as R11 and R22. Then what our gain and input and output impedance will be with feedback, and then just what is the input and output impedance of this amplifier without the loading effects. Okay, if the loads are not given, Rin and Rif is the same, and Rout and Rof is the same value. Okay, but that is if they are not given. Our second problem will be like that. Okay, so the first thing to do is to have a look at our feedback network. So if we redraw it, here is V out, and V out goes into our network. That is the input to our feedback network, and right here going into the inverting terminal of op amp is Vf, so that is the output of our feedback network. So you can redraw it immediately like this, and we will see that this is just a voltage divider. So Vf is R1 over R1 plus R2 multiplied by V out, and that is just your beta network then. It's the voltage divider. So 1k over 1k plus 1 meg is 1 over 1001. 1 over beta would be 1001 then, so this network strives to have a feedback gain of 1001. Okay, but that is only if an amplifier has the infinite amount of gain available. So this is what our gain would be striving towards. Right. R11 would be when we short this source out and look into the amplifier right here. And if we do that, we will see R1 and R2 in parallel with one another. So 1k and 1 meg, so roughly 1 kilo ohm. And when looking into this side of amplifier, we see these two resistors in series with one another. So R22 is R1 plus R2 is 1001 kilo ohms, and that is approximately 1 mega ohm. Right, so that is our beta and R11 and R22. So if we make our operational amplifier model, so this is the input impedance of our op amp, this is the gain and output impedance of our op amp, and we need to apply R22 and R load. See, this is happening in shunt, and here at the input everything is in series. Right, so the aim at this point is to find Rin, and Rin would be the sum of all three these resistors. So a 10k plus 100 kilo ohms plus a 1k is 111 kilo ohm. And if this source is switched off, R out, R22 and R load is everything in parallel with one another. And that will give us 666 ohms. So what's that? 1k, 2k's, and 1 meg. So that gives us the input and output resistances without feedback applied. Now, the gain of this amplifier. We are going to take all the loading effects into account here. So A would be the differential gain of this amplifier multiplied by the voltage sitting over this resistor right here. the input differential resistance. Okay, so AD is the main gain factor. Doof. Okay, then there is voltage division happening on the input side, and we are trying to find VID. So that is just RID over all the resistors on the input. So RID over Rin. That is our loading factor on the input side. You could also have done this as RID over Rsig plus RD plus R11 as a very long equation. Just since we have Ri available, it gives us what we want in any case. So that is the input loading. The output loading is that a portion of a voltage will sit across this output impedance right here, and not everything will go towards the load. So we have a voltage division on the output. So R22 and R load is in parallel with one another, having the same voltage sitting over them. So R load parallel to R22 over R load parallel to R22 plus R out. Okay, so voltage division on input, voltage division on output. My, it is a voltage amplifier. So typically those are voltage divisions on input and output when we are doing loading. For current amplifiers, it will be current dividers. Right. So, main gain element, and then all the loading factors will give us our A of our amplifier. And note that this includes R11 and R22 in it. Right, so these factors multiplied with the gain that we had, with 10 to the power of 4, will give us 6000 volts per volts gain. So there is already a reduction in our gain due to all these loading effects. Right, but with that we have everything to calculate our input impedance with feedback. So 111 kilo ohms multiplied by 1 plus 6000 over 1001. Our input impedance will be 776 kilo ohm. So that is an increase on our input impedance. There should be a decrease on our output impedance. So that's 666 divided by 1 plus A beta is 95.2 ohms. If we calculate our feedback gain, so A over 1 plus A beta, we get to 857.9 volts per volts. And if we look at this feedback factor right here, we are striving to be at 1001 volts per volts. Okay, but our gain is not infinite, so this is a reduced amount right here. So with a better choice of feedback resistors, you can probably achieve 1001 because there is 6000 available. Right, so by adjusting your resistors, you can get to the 1001 that you want. But note that we didn't get there with resistor choices. Okay, so whenever you're applying feedback and it doesn't work out, just adjust your resistors. Right. So the input impedance and output impedance without loading. So Rin would be our impedance with feedback minus our signal resistor. So that is just 766 kilo ohms because they are happening in series. And our output impedance right here is in parallel with our load. because it's a shunt configuration. So our output impedance, we just do a reverse parallel configuration, and our output impedance without loading effects will be 100 ohms. Okay, so this is how you find the input and output impedance of your amplifier without the loading effects. On to a second example. Okay, so our second example doesn't have any loads. Then it is two MOSFETs biased to have a transconductance of 4 milliamperes per volt. The output impedance of our MOSFETs is infinite, and the drain resistors used is 10 kilo ohms. So, first thing, without loads, our input with feedback and our output with feedback is our amplifier's input and our amplifier's output impedance. Right. Now, first order of business, find A, beta, and the input and output impedance. Then second order is to find it with feedback. So right here we have two common source amplifiers cascaded. Right. So we have two amplifiers. One is going to have degeneration and the other one is just going to have a loading of a feedback network. Right. And again, look at this. It is a voltage divider like that, and the input, it is happening in series. So, series shunt. First order of business, analyze the feedback network. It is again just a voltage divider. R1 is 1 kilo ohm, R2 is 9 kilo ohms, and that will give us a feedback factor of 1/10. So the gain of this amplifier should strive to be about 10 volts per volts. Okay, R11 is R1 parallel to R2, so 1 kilo ohm in parallel with 9 kilo ohms gives us 900 ohms, and the sum of the two gives us 10 kilo ohms. So R11 and R22, and the beta is calculated. Right. So R11 will be sitting at this point right here. And R22 will be sitting as a load to our amplifier right here. And this nonsense here in the middle will disappear. Okay, so R11 is going to act as a degenerative resistor for this first amplifier right here, and R22 is going to act as a load for our second amplifier right here. And to make some observations, our in of this amplifier is infinite because it's a MOSFET. So we can multiply that with 1 plus A beta as much as we like. It stays at infinite. So Ri and Rif would be infinite because it's a MOSFET. R out should be the parallel combination of all the output impedances right here. So that would be RD2 parallel to R22 parallel to R out of this MOSFET, but R out of this MOSFET is infinite. So R out is just 5 kilo ohms, 10k in parallel with 10k. The loading factor between the two amplifiers is 1 because we have infinite input impedance looking in this direction. So if this were BJTs, it would be good to consider the loading factor between the two PJTs. Right, so using MOSFETs here makes our life easy. Now, we can determine the gain of a first amplifier and the gain of a second amplifier, and with that get the entire gain of our system. So, gain 1, amplifier 1, would be the transconductance multiplied by the drain resistance divided by the degenerative effect here of R11. So A1 is minus GM1RD1 plus GM1R11 at the bottom. That gives us minus 8.696 volts per volts. The second amplifier with the loading of R22 is GM2 times RD2 R22. We could have called this R out if you wanted, and that gives us minus 20 volts per volt. So the gain of this amplifier from input to output without feedback applied is 173.9 volts per volts. Right, so the input impedance is infinite. The output impedance should decrease, so it's 5k divided by 1 plus 173.9 divided by 10, and that gives us output impedance of 272. So going from 5 kilo ohms to 272 is a very big decrease in output impedance, and it takes us from having an amplifier with a very large output impedance to something better suited as a voltage amplifier. Okay, the gain with feedback, if we calculate this, that is almost 10 volts per volts, which our feedback is striving for. Okay, so large input impedance, low output impedance, and again that is almost stabilized to the point where we want it. And that is it for voltage amplifiers. Voltage amplifiers is probably the easiest of the bunch. So yeah, I hope that this is helpful, and see you in a next video where we are going to do the current amplifier. Thank you for watching, and see you in the next video.